In most nooks and crannies of the world, if we look close enough, we'll probably find some math lurking around, as we've been seeing throughout the series. Take our bodies, for instance. Across all the people within each country, when we plot the data, our heights, shoe size, even the surface area of our skin all end up being distributed in about the same way. That's pretty wild, no matter how much math you know. And the same pattern is hiding all over the place, from the rolls of dice in Dungeons & Dragons to standardized test scores. But in order to see that pattern, a lot of the time we have to do some tinkering to connect reality to the math we know in order to solve all kinds of problems. I'm Jason Guglielmo, and this is Study Hall Real World College Math. The more you start looking at things through a math lens, the more you can untangle complex patterns of information, solve problems, or even admire the hidden structures and logic buried everywhere. But it's not always obvious how to do that right away. No need to fear though. In math, we can often tackle hard problems by starting with something simpler that we do understand. For instance, let's explore that bell-shaped pattern we mentioned in the intro, and why they show up so often. They might look familiar, since last episode we talked about normal distributions, which is what we call data that gives us a particular bell-shaped curve when we plot it based on frequency. This bell-shaped curve also tells us about probabilities, which we'll get into more in a second, and it's defined by two numbers, a mean and a standard deviation. Like, say you were recording the body weights of newborns in a population, which doctors and public health professionals look at to study the health of babies. Birth weights broadly follow a normal distribution. And in the US, that distribution for babies born at term has a mean of 3.4 kilograms and a standard deviation of half a kilogram. The mean tells us where the center of the distribution is, and in this case, the average weight of a baby. And the standard deviation tells how spread out the data is around that center, which in this case is broadly how much we expect weight to vary between newborns. So both the mean and the standard deviation affect the shape of our curve. Last episode, we focused on a particular normal distribution called the standard normal curve, where the mean is 0 and the standard deviation is 1. And as we learned, we know a lot about standard normal curves, so we can use them to work with all the other normal curves we might find. Like, by finding the area under our standard normal curve, we can talk about the probability that data falls above or below some point in our data set. We do this using z-scores, which we talked about last episode. Check out that episode for a refresher. But basically, a z-score tells us how many standard deviations a particular point is from the center of the dataset. Like in a dataset about the weights of newborns, we might be interested in how many babies have a weight less than 2 standard deviations below the mean. We can look up that z-score in a z-score table to figure out the area under the curve up to that point, which gives us the probability. So if we look up -2 in a z-score table that tells us the area under the curve to the left of that point, we'd get 2.3%. And that means there's about a 2.3% probability of any given newborn in the US weighing less than whatever weight is 2 standard deviations below the mean. All of this is pretty important because when we're looking at distributions and the shape of a dataset, figuring out how likely a point is to be in our set or how likely something is to happen is a big part of why we care about distributions at all. Unfortunately, to use z-scores, we need to know about standard deviations. And the standard deviation of a data point isn't as obvious when we're not working with a standard normal curve, which is most of the time. Like, rather than talking in terms of standard deviations, we might want to know something like how many babies are born with a weight less than 2.5 kilograms. To answer questions like these, we need a way to connect our idealized math world to the kinds of distributions we'll find out in the wild. Fortunately, in math, when we're trying to solve a complicated problem, we can use what we already know about a simpler case. And it turns out we can adjust the standard normal curve in order to find z-scores and make exactly the same kinds of probability calculations for any normal distribution we find in the wild. It's actually fairly simple to adjust bell-shaped curves. Depending on our new mean, we can move it around the x-axis. And depending on our standard deviation, we can stretch or squeeze it to fit our data. To see how we do that, let's check out custom wetsuit designer Aria, who's trying to forecast the costs for running her new business. Aria's wetsuits are tailor-made to size. From taking measurements, she can estimate the surface area of a customer's body, which tells her how many sheets of neoprene she needs for each order. A suit usually requires between 3 to 6 sheets of neoprene, but she can't order in bulk ahead of time because each customer has different requests for how thick the material is, style, and color. They are bespoke after all. On average, her male customers tend to be a bit larger, and occasionally she finds that some of them require at least 7 whole sheets to make a suit. And as it happens, her supplier just announced they'll offer a discount when ordering 7 or more sheets. So, Aria wants to know how often she'll get this discount on her neoprene orders for male customers. To help Aria make sense of this, we need a couple of details from Aria's records of her previous customers. First of all, we need to know how much material she used for each of her previous wetsuit orders, which depends on the body sizes of different customers and how that data is distributed. She doesn't have a ton of historical data, so for the most accurate probabilities, she also looks up information on how people's body shapes are distributed. As it turns out, we've studied it a lot, and for a given gender, the surface area of human bodies follows, hey, what do you know, a normal distribution. And since the material for each wetsuit depends on the size of the person, the amount of material she's used for each suit also follows a normal distribution. From her customer records, the distribution of the neoprene has a mean of 2.6 meters squared and a standard deviation of 0.2 meters squared. We then need to know how the amount of neoprene corresponds to the number of sheets Aria orders. Well, the sheets come in units of half a meter squared, so if a customer needs more than 3 meters squared, it takes 7 or more sheets. So now that she knows that the amount of neoprene she orders is normally distributed, and that any order that needs 3 square meters or more qualifies for the discount, she can use that information plus the power of z-scores to figure out how likely it is an order will qualify for the discount. Basically, Aria will calculate the area under the curve to the right of 3 on the x-axis. That will give her the probability an order needs 3 square meters or more of neoprene, which are all orders where she gets the bulk order discount. Now comes the clever part. Remember, on the standard normal curve, where a data point is along the x-axis is the same as how many standard deviations it is above or below the mean. So by transforming our normal curve into a standard normal curve, we can find how many standard deviations each point is away from the mean, which is exactly how we define z-scores. And then we can use that to calculate the area under the curve. In particular, since we're looking for people with body sizes 3 meters squared and higher, we can work out how many standard deviations 3 is above the mean. First, we need to subtract the mean from the point we're interested in to get the distance between the two numbers. If we do this in general for the entire curve, we could write it using statistical notation and call our mean mu and our particular value x. Doing this shifts our whole distribution and recenters it on 0. Things are already looking closer to our standard normal curve, only the spread of the distribution isn't quite right. Right now, our standard deviation is still 0.2, but we need to make some adjustments to make it 1 if we want to find our z-score. To see how, let's look at where the point that used to correspond to 3 square meters landed on this new distribution. After subtracting the mean, it winds up at 0.4. And to figure out how many standard deviations that is away from 0, our new center, we simply divide everything by our standard deviation. It's like seeing how many 0.2 segments will fit between the mean and our data point, and that will expand our data to fit the standard normal curve by stretching out all the points from the center. Now, we've transformed our curve into the standard normal curve, and we know that our point is 2 standard deviations away from the mean. And that's also exactly the same information we use when calculating z-scores. So here's the great thing. The probabilities we calculate for the standard normal curve using z-scores will also be the exact same probabilities we need for any normal curve, so long as we make these adjustments. So, to sum up, when we start off with some variable or data that follows a normal distribution, we can get the z-score for every possible value by transforming our normal distribution curve into the standard normal curve. We do that by subtracting the mean and dividing through by the standard deviation. In Aria's case, to get the probability of needing more than 3 meters squared of neoprene, she looks up the z-score probability for 2.0 in a z-score table. Because of how the left of the tail table is set up, that gives her the probability of someone needing less than 3 square meters. So she then subtracts that number from 1, since she wants the probability under the curve from the right of that point, where all the values are larger than 3 meters squared. That gives her a probability of just over 2%. So that means she can expect to get a discount on neoprene for about 1 in every 50 orders. And with that knowledge, she can plan her operating costs for her new business. In general, the ability to change between any arbitrary normal curve and the standard normal curve gives us a kind of mathematical bridge for calculating probabilities about any normal distribution we come across. When we subtract the mean to move the graph up and down the x-axis, or divide through by the standard deviation to stretch or squeeze our data, we're manipulating our graph to fit our standard normal curve. This makes it easy to see why the standard normal curve is called standard. We can use our formula to map a normal distribution onto it, and then use z-scores to calculate things about them. How body size affects business forecasts is just one example that highlights the power of statistics. Normal distributions pop up all over the place, from measurement errors in physics to other factors about people's body shapes, and even test scores. But with the right math tools, we can make sense of them all. Overall, the statistics and probability we've explored in the last few episodes gives us ways to interrogate the world and take steps towards understanding variety, uncertainty, and chance, which most of the interesting and unusual things we want to learn about in life will involve. And like we saw for Aria, one of the many places where we make sense of the future with math is the world of finance, which is where we're headed next episode. Thanks for watching Study Hall Real World College Math, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video, give us a like and subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See you next time.